Okay, this box problem is like the classic calculus optimization problem. So they tell you that you've got cardboard that's 4 centimeters by 7 centimeters, and you're going to cut these little squares out of the corners. And when you cut those squares out, you'll be able to fold up the edges, and you'll make a box that'll look like this. And what you're trying to do is find out how big should these squares be, so that you get the largest volume of the box as a result. So what we have to realize is as we do this, if this original dimension here was 4 centimeters this way and 7 centimeters this way, what we're going to do is cut squares out. We don't know how big they are, so we're going to say they're x by x centimeters. So each one of these things would be x by x, and the question is we got to figure out what x is. So maybe it's a 1 by 1 inch square that we cut out. We fold out, cut out those corners and fold up the edges. Or maybe it's 2 inches that we cut in. Obviously, actually, it can't be 2 inches, because if you cut 2 inches in this way and cut 2 inches in that way, you're not going to have any width to your box left. So they usually ask you in these problems that there's a domain kind of involved here, and the amount that x can be cut, it has to be more than 0, but it has to be less than 2. You got to cut out something so that you can fold up the edges, but you can't cut out any more than 2, because otherwise you'll have no width left. So I'll just throw that in here as a little extra, that x has to be something between 0 and 2. But what's going to happen is the box that results, this width, which is this distance here, it was 4 inches, but you've cut x inches off this side and x inches off that side, so it's going to be 4 minus 2x along that side. And then similarly, this dimension over here, it was 7 centimeters long, but now it's going to be 7 minus 2x, because we lost x on this side and we lost x on that side. So the dimensions this way are 7 minus 2x, and then this is what's cool about this, is the height of this box that you get is going to be formed by this squares that get cut out. So once you take this edge and fold it up that way along this little perforation that you'd find there, that box will be x centimeters tall. And if you remember the formula for the volume of a box, it's just length times width times height. So I'll put length times width times height. But the length is, let's say, 7 minus 2x. The width is 4 minus 2x. And the height is x. So foiling these guys together, let's see, you're going to get 28 minus 14x minus 8x's is what? Minus 22x's, and then plus 4x squared. And that's being multiplied by x. So that would be 4x cubed minus 22x squared plus 28x. And that's the volume function. And, that's a cubic, so it's probably going to look something like this. And you want to find out when that's going to have its maximum. And so you're really looking for this. I think this graph, if you actually graph that function, it would kind of look like this. And when x is 2, that thing's going to have a 0, because it's going to be making that factor 0. And it's going to have another one at 3.5. That's when that factor 0. And it's going to have one at 0, which is where, when x is 0. So you're trying to find that spot where this is the volume, and you see that the volume goes up, and then it starts to come back down. And of course, the way you find the maximum of a function is you find out where the slope is equal to 0. So we're going to take the derivative of this thing, dv dx, which is 12x squared minus 44x plus 28, and you set that thing equal to 0, and good luck with that. Let's see, there's a factor of 4 in that, so we could divide through by 4 and get 3x squared minus 11x plus 7, and find out when's going to make that equal to 0. And I think there was a note in the directions that said the answers are going to turn out to, it's not going to be a nice number, which makes sense because this does not factor. That quadratic doesn't factor. So the way to find the solution is you can use the quadratic formula. So you get x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. And let's, God knows what that's going to be, 11 plus or minus the square root of 121 let's see, 12 times 7 is 84, so 121 minus 84 all over 6. 121 minus 84 is like 37, I guess. So it's 11 plus or minus root 37 over 6. Now, the square root of 37 is about 6 or so. It's going to be a little bit bigger than 6. So 11 minus 6 over 6 is going to be about 5 over 6. That's going to be a little less than 1 inch. That's probably the answer, is 11 minus root 37 over 6. I think 11 plus root 37 over 6, let's see, that's going to be about 3. Yeah, that's going to be outside the domain. So, in other words, 11 plus root 37 over 6 is going to be bigger than 2. So that means it's not a possibility. Now, to show that that is actually a max or a min, you'd probably want to do the second derivative test. You could do v double prime, which is 24x minus 44. And remember, that's telling you, the second derivative tells you about the concavity of the curve. So if you plug in this number into that, what's going to happen is you're going to wind up getting a negative number, I believe, because that number is going to be a little less than 2. And so you're going to get something that's less than 0. And because the second derivative is less than 0 at that number, 11 minus root 37 over 6, that means the function's concave down. But yet we already know that it has a slope of 0, so that is a recipe for a maximum. So that's going to tell you your max volume is going to occur at 11 minus root 37 over 6. I know I kind of went quickly through that, that solution there as far as the quadratic formula goes, and then ballparking about what this value would be. But then, trust me, do it on a calculator, and you'll find out that that's going to be the good number, I think.